Okay, I'm going to shift now to the last talk of the day, which is going to deal with nonlinear analysis. Okay, any questions on the equivalent linear analysis? Before we move on?
Buenas tardes. Entendiendo que el análisis equivalente lineal Buenas tardes. Entendiendo que el análisis equivalente lineal no es aplicable para análisis dinámicos de presas, ¿qué modelos recomienda para este tipo de análisis en presas o presas principalmente?
Well, the most commonly used analyses for dams for two-dimensional equivalent linear analysis is generally the FLUSH program. It's developed at Berkeley. It's a two-dimensional finite element program. There is also the SASE program. You can perform equivalent linear analyses in other codes as well. We'll talk about some of those on Wednesday when we talk about two and three-dimensional analyses. There are the FLAC program can be used in an equivalent linear mode, but you need to write some instructions in the FISH language that comes with FLAC in order to operate it that way. Quad 4M, yes. I knew there's one I was thinking. Thank you. There's a program called Quad 4M that is a two-dimensional equivalent linear program. It's written by Ed Idris and modified by Martin Hudson. It is equivalent linear and it operates in the time domain. So it uses integration and time steps in order to calculate the response, but it is an equivalent linear program. That's probably the one that is used the most, I think. I was blanking on the name of it. That's available and widely used for dams. When I've done analyses of dams, I've run Quad 4M in parallel with nonlinear codes and run them together, first scaling the ground motions down to weak levels to make sure that they're giving the same response, and then increasing the ground motion levels. So that's an approach that I've used for those kinds of problems.
Steve, you mentioned Quad 4M, the latest edition, so much better. Marty Hudson has a newer version, it's Quad 4M.
That remind me, because I don't know.
Don't use the original Quad 4M because they've done a better job of matching the frequencies. You have to use Rayleigh damping. And so Quad 4M plus, with some extra numbers after it, by Marty Hudson, who's been the person who's continued to run with it, get the latest version of it if you're going to run Quad 4M plus, whatever it is.
Quad 4M was what I thought the Quad 4 was the original and Quad 4M was the improved.
And then they made a P.
You did, okay.
And letter.
I haven't seen the P. Okay, so let's go ahead and start our last session dealing with nonlinear analysis. If we're going to perform a nonlinear analysis, we're going to perform it typically when we have either weak soils or very strong motions where we're expecting a lot of nonlinearity. We will, in order to handle damping, analyze a slightly different equation. We'll use a an equilibrium equation as we have derived before. We're going to have shear stresses on the left side and displacements on the right side. And if we're going to treat our soil as a viscoelastic medium, in order to have a small amount of viscous damping, we'll introduce a viscosity term here in most of our codes in order to avoid the situation of being undamped at low strain levels. So we're going to also subdivide a layered system into a series of soil layers and sublayers. So we'll take our individual layers and we'll cut them into smaller sublayers, and we're going to need to subdivide time into a set of time steps. And so we'll do that as well. And so we have a grid now of position and time. We can take our soil profile away, and we're going to need to calculate the response at every intersection point here, every depth and every time. And so if we look at a particular time, say at a time t sub j and a depth z sub I, there will be some state of that soil and some state of its dynamic motion. There's lots of different ways in which this these types of analyses can be performed. We're going to be interpolating spatially with respect to depth, and we're going to be integrating numerically with respect to time. There's a lot of different ways that we can do this, so I'll describe very briefly one of them, but it's certainly not the only way of doing things. If we know the velocity at depth z sub I and time t sub j, we can call that v sub ij. We can make an estimate projecting forward of the velocity halfway across the next time step and use that to calculate the displacement at the next time step and the velocity from that. So we move from time step t sub j to time step t sub j plus 1. There's more steps than that, but that's basically what we're doing in this integration process. If we do that for all of our time steps, we'll improve from knowing the conditions at time t sub j to knowing the conditions at time t sub j plus 1. If we've done that, then we can change the properties of the material. And so during this time step, there's been some displacement of each node in our profile, which means there's been some strain occurring. And if we have a nonlinear model for our soil, a nonlinear stress strain model, a constitutive model, we can change the stiffness to be consistent with the new level of strain that exists in the soil. And we can use that then for the next time step. So our adjustment to the stiffness can depend on the strain amplitude, the strain history. There's a whole bunch of things that we can take into consideration here. We can move then, repeating this process from time step t sub j plus 1 to t sub j plus 2. We can go to the next time step and the next time step and continuously repeat this process until we've worked our way through the entire ground motion. We've adjusted our stiffnesses throughout this process. While the actual behavior is smooth and continuous, we're going to use a series of discrete time steps with constant stiffness in each of the time steps, but adjusted between the time steps to approximate that smooth and continuous behavior with a series of linear segments. And so the smaller our time steps, the more accurately we'll be able to represent that actual continuous behavior. So in a very simplistic sense, this is what we're doing in a nonlinear analysis. You can see that we have actually modeled a stress strain loop here. And so the hysteretic damping that occurs due to the hysteretic behavior of the material is automatically being accounted for. We don't need a damping curve now because we're modeling the hysteretic damping directly. So there are some advantages to this approach. We're working in the time domain now, so we can change the properties after each time step to model nonlinearity. In the frequency domain, the amplitudes of all those sine waves in that frequency series and the response of the transfer function is the same all the way from the beginning to the end. Nothing can change in time there, but we can in a nonlinear analysis in the time domain. We can also formulate our model in terms of effective stresses. So we can model the prediction of, the generation of pore pressures. And we can couple that with a solution of the diffusion equation, or the consolidation equation, to model the dissipation and redistribution of pore pressures. And that's important when we have liquefiable soils. And with good constitutive models, we can start to understand the way liquefiable soils are going to behave, how they're going to affect ground motions, and how they're going to affect both cyclic and permanent deformations. So we have to use these if we're dealing with liquefiable materials. They also avoid resonances that can develop in equivalent linear analyses. While we're approximating nonlinear behavior in an equivalent linear analysis, it's important to remember that each analysis, including your final analysis with strain-compatible properties, is a linear analysis. The stiffness of the soil is not changing from the beginning of the earthquake to the end of the earthquake. The damping characteristics are not changing. And that can lead, when we have a constant stiffness, there can be preferential frequencies at which we tend to build up strong motions that won't exist in a nonlinear material because the stiffness is always changing in a nonlinear material, so we can't have resonance there. We can compute permanent strains in a nonlinear analysis, which means we can compute permanent deformations, and that's what we're often interested in. How much is something going to move? So nonlinear analyses, if they're done properly, can produce results that are consistent with equivalent linear analyses when they should. That is, when we don't have large degrees of nonlinearity, when we have small to moderate strains. And when the strains become large, they're more accurate than equivalent linear analyses are. And they can do things that equivalent linear analyses can't do. They can do pore pressures and permanent deformations. If we compare the results of equivalent linear and nonlinear analyses, we can take a look and see how they behave relative to each other. So I'm going to look at a profile here that is 30 meters thick. We're going to put an input motion in at the base, look at the motion that we achieve at the top in terms of time histories and response spectra. We'll also look at strain behavior at location near the surface, one just above the rock level and in the middle of the profile. The input motion is just kind of a generic motion. The Topanga record from the Northridge earthquake has a nice, relatively smooth spectrum. If we scale that Topanga motion to peak accelerations of 0.05 G, a pretty low level of shaking, and analyze it using equivalent linear analyses, which results of which are shown in red here. I did this using the Crochet program, which is the one that I demonstrated a little earlier, and using a nonlinear code that I have worked on, and I'm still working on. That's called Crochet NL or PSNL. We can see, in this case, we have a weak motion in relatively stiff soil. So we expect the strains to be low. We expect then a low degree of nonlinearity, and we should expect that the responses are going to be similar to each other. They will differ due primarily to differences in damping characteristics at this stage and how damping is modeled, and we get a very, very close agreement between them. So this is a very good result, at least in terms of showing us that the equivalent linear model is giving equivalent results to the nonlinear model, and vice versa. It's a good check on the nonlinear model. It should give good agreement with the equivalent linear model for these types of conditions. If we look at the velocity history, very good match. If we look at the response spectra, very good match. If we look at the stress strain behavior in the lower right, we can see that there's not much nonlinearity in each of those locations at 1 meter, 16 meters, or 29 meters. And so we should expect that we get pretty good agreement under these conditions. If we scale the motion up to 0.2 G, now we have a moderately strong motion, still with stiff soils. We have relatively low strains, still relatively low degrees of nonlinearity, more than we had previously, and we should see a similar response. And we do. You see there's pretty good agreement between these, but we can look closely and see some places where the equivalent linear analysis is over-predicting the results that we get from the nonlinear analysis. And we see it here in the accelerogram, that some of these spikes are higher in the equivalent linear, the red signal, than they are in the black. And even in the velocity history, if we look closely, we can see that as well. And these are the spurious resonances that I spoke about before. The linear analysis will build up high levels of response at certain frequencies. The transfer functions can become quite high because the stiffness isn't changing and these waves can build up at certain frequencies. And in a nonlinear material, if the amplitude starts getting strong, the material becomes softer. The frequency changes and you can't have a resonant condition in a nonlinear material. We see it here also in the response spectrum. So you can see at certain frequencies, the equivalent linear analysis is giving us a significantly higher response than the nonlinear analysis would. So these are these resonances that can occur at certain frequencies. If we look at the stress strain behavior, up near the surface, the shear stresses are low because we're very close to the surface, and the strains are low. And so there's not much nonlinearity. We're seeing some softening of the profile here at the middle, and we're seeing more and more complicated behavior down just above the bedrock level. So if we look at this one carefully, we can see that the stiffness is changing more here than it was at the other depths. And that leads to some of the differences that we see here. If we go up to 0.5 G, now we've got a strong motion in the stiff soil, we've got moderate strains, moderate nonlinearity, and we get, and those are the different response. It's different at the beginning of the ground motion, it's different in the middle, and it's different, maybe not so much different towards the end. Response spectrum, we're seeing a lot of over-prediction at about 26 seconds or so in the equivalent linear analysis. If we look at the degrees of nonlinearity and stress strain behavior, we see that we're getting responses showing much more nonlinearity, particularly in some of the cycles. When we go up to 1G, now we're seeing even less agreement, particularly at the beginning of the motion. You can see that our nonlinear model is predicting the black response, pretty stiff behavior. We're seeing some significant accelerations early on, and the equivalent linear is not predicting that at all. The reason for that is that the stiffness of the equivalent linear model is being controlled by the peak strain. We reduce it to an effective strain, but that strain is controlling the stiffness that we use for the entire motion. Well, that strain probably doesn't occur until maybe this part of the record or so. In reality, this is showing us that our equivalent linear analysis is assuming that the ground has been softened before that peak strain has ever occurred. And so it's unrealistically soft here in the early part of the record. Then as we move further into the record, in the stronger part, that linearity is causing us to over-predict the response. And then at the last part, we're still over-softened, and a nonlinear material will retain some stiffness even after it's undergone large excursions, large strains, and we're under-predicting the response again with the nonlinear. And so with the equivalent linear model. And the response spectrum not very good, and we're seeing a lot of complex behavior there. We can torture this profile a little more by assuming a velocity contrast, say at a depth of 16 meters, so just below this 15-meter recording that we've been paying some attention to. So now we're going to go from 762 meters per second bedrock to 300 meters per second soil to 100 meters per second soil. So we have another impedance contrast in there. If we, I think this is still the 1G input motion, what we're seeing now are very large strains near the bottom of that upper layer. And again, when waves come from a stiffer material into a softer material, we see that the deformation amplitudes increase and the strain amplitudes will increase under those conditions. And they're doing that here. We're getting much larger strains on the order of 6% shear strain down at this level, anticipating a lot of energy there. The ground motions of the surface are very different. Our equivalent linear model is going to converge to a very low shear modulus at the bottom of that upper layer, a very high damping ratio, and high frequency components just can't get through. That layer will become so soft that the upward traveling waves hit the bottom of it and they just get reflected back down, and very little is transmitted up to the surface. So you see this kind of response. Here's our comparison of the red and the black. The equivalent linear analysis is just no good at all under these conditions. So we're seeing very soft behavior at the beginning of the earthquake before anything to soften the soil really has happened. So more consistent in the middle, but still not very good at all. And response vector reflecting. There was a very nice study done a number of years ago by John Stewart at UCLA and his student Andy Kwok, where they compared nonlinear analyses by a number of different computer programs and different investigators. They ended up working with 5 existing nonlinear codes, and they hired the developers of those codes to run them and to comment on their results. They also had an advisory committee that I was on to look over these analyses and help interpret the results of them. And there were regular meetings between the advisory committee and the developers, and it was very useful for understanding some of the strengths and weaknesses of the different computer programs and the protocols for how they should be used. There were a whole series of codes that were considered. These are the ones that were ultimately used. Deep Soil, developed by Yusuf Mishash and a whole series of students at the University of Illinois, is a very widely used, commonly used program. It's a derivative of a program called Gesra that was developed by Liam Finn many years ago. DMOD 2, Mladen Vucetić and Neven Matasevich worked on that. It also comes from Gesra. OpenSeas is a large finite element code developed by the Peer Center that can be used for one-dimensional analyses. SUMDIS is developed by a fellow that was at UC Davis, and then I think Geomatrix, and then TESS is a program with Don Pikes. DMOD 2 is an enhanced version of DMOD. It uses a lump mass model from Gesra, and it requires Rayleigh damping. Rayleigh damping has a mass proportional and stiffness proportional terms, so the sum is frequency dependent. And so there are some issues involved with choosing the right way to implement Rayleigh damping in order to use these types of codes, because damping is not a frequency dependent phenomenon. The people working on Deep Soil have spent a lot of time and effort on improving this aspect of their particular code, and have made a lot of improvements there. So they have more advanced Rayleigh damping and frequency independent damping options now. Once again, it's a lump mass program. TESS is actually a finite difference program, so it solves the wave equation directly by integration. It has a different unloading, reloading system. OpenSeas is a finite element model that has quite strong capabilities. It's just usually the fraction of those capabilities here, but it has much more advanced constituent models. Uses Rayleigh damping as well. SUMDIS is finite element, uses simplified Rayleigh damping and bounding surface plasticity model. They made a number of recommendations at the end of this project, one of which was how to specify input motions, because they found that people were doing it very differently. Even people who have a lot of experience and expertise with this. If you're using outcropping motion, use the motion, apply it as an outcrop motion with an elastic base. So that elastic base will absorb some of that energy. For a motion that's recorded at some depth, you want that motion to be the motion that's applied, so you apply it as a within profile motion with a rigid base. For viscous damping, recommended using full or extended Rayleigh damping as they were described at that time. iterate on the selection of control frequencies at which you're going to specify the curving Rayleigh relationship to go through. They recommend, when you can, to iterate, to select that, to essentially match equivalent linear response, where you can, in equivalent linear analysis, you can put in frequency-independent damping. If you can't, they recommend using Rayleigh damping, controlling the damping ratio at the natural frequency of the soil deposit and 5 times that natural frequency. So again, we have this frequency-dependent Rayleigh damping thing. For backbone curves, it's important, as I had mentioned earlier, to adjust them so that you have the correct shear strength. If you simply extrapolate based on Darandelli's model or any other model that's based on a hyperbola or a modified hyperbola, it's not necessarily going to have anything to do with the strength that you have. And you can over-predict your strength or under-predict your strength, either which is a good situation to be in. So there are a variety of procedures that have been implemented into some of these codes to achieve a backbone curve, or achieve a backbone curve that captures the correct strength of the material that you're using to specify. They ran these codes against some vertical array data and found they were producing reasonable results, but over-damping at high frequencies in a number of cases and over-amplifying at the natural frequency of the site. The variability of their predictions was most significant at short periods or high frequencies, which is kind of what we would expect to see. The model-to-model variability was most pronounced there as well. Nonlinearity was modeled fairly well up to the levels for which data was available, up to about 0.2 G or so. But we're really trying to get more data where high degrees of nonlinearity have been observed. We need a good, strong shake in Berkeley or somewhere where we have some weak soils, San Francisco Bay Buzz and things of that nature, and where we have instruments. Deep soil, DMOD2, and open seas produce similar behavior. Test was different. Some just had difficulties. Deep soil, I think, is now the most commonly used program for 1D site response analysis, 1D nonlinear site response analysis. There's a lot of effort. There's been a lot of PhD dissertations that have gone into that program. It's with pretty refined code. DMOD2 is a competent program as well. And a lot of the more advanced codes like OpenSeas, FLAC, Plaxis can also perform one-dimensional analyses as well as two, and in some cases, three-dimensional analyses. The wildlife site we talked about before as one that had a liquefiable soil profile. It exhibited very stiff behavior with high frequencies being transmitted through the soil layers in the first 13 to 14 seconds of the ground motion. Then there was a transitional stage after which only low-frequency motions were making their way up to the surface. And then there was a weaker shaking afterwards. It was observed that there were in the one instrument, pore pressure recording that the developers of that site considered to be producing reasonably accurate results. There were some points in time where the pore pressures dropped, and they dropped at times that coincided with kind of unusual, at least at the time, looking spikes in the acceleration profile. And this is due to dilation of the soil as the stress state passed the phase transformation, a quasi-steady state condition, and the soil started to dilate. We'll talk about this a lot more when we talk about soil liquefaction. But this is a very important finding, and it has led to some very good improvements in our modeling of the behavior of liquefiable soils. Here are, I mentioned earlier this morning that the Elbow Ranch earthquake occurred. That was a magnitude 6.2 that did not cause liquefaction. And so you see here both measured and predicted motions in the east-west and north-south directions. The measurements are the measurements that were made at the surface. The predictions are predictions using the code that I have worked on. So we get a pretty good agreement. The next day, the Superstition Hills earthquake occurred. It is cause liquefaction. This is a better plot than the one I showed you previously. High frequencies early on, low frequencies later in the record. Something funny was happening in between. There was a transition from high frequencies to low frequencies. If we look at the Elmore Ranch record where no liquefaction occurred, we can use techniques to break down, different techniques to break down ground motions. We often use Fourier series to look at the distribution of frequencies, but we can use time frequency analysis to break down the change in frequencies as functions of time. So these kinds of time frequency analyses can be done in different ways. What I'm showing here are ratios of wavelength amplitudes, and they show that high frequencies are being transmitted up to the surface, essentially all the way through at least the first 30 seconds or so, or maybe 30 to 40 seconds, of the Elmore Ranch record. So these are records of we did a wavelength transform on the surface motion, wavelength transform on the input motion, and took the ratios. So we can see that there's some low frequency motion here throughout, and we can see high frequencies extending over most of that record. When we do the same thing for the Superstition Hills record, we can see that our high frequencies are there in the first 13 to 14 seconds, and then boom, they disappear very quickly. They come back periodically when we see these higher frequency dilation pulses occurring. But the stiffness of the profile and its ability to transmit high frequency ground motions up to the surface disappeared at 13 to 14 seconds. And we interpret this as the triggering of liquefaction. That the soil profile became very soft. All it could transmit, and you barely see it down here, are very low frequencies up to the surface at that time. And so if we analyze the Superstition Hills record with a nonlinear effective stress code and one that can handle phase transformation behavior, we can see that we model this kind of, we have the capability of modeling this behavior pretty well. But we have to have a good constituent model that can do that. Some of the available nonlinear programs do, some of them don't. The deep soil code has a pore pressure generation model in it that's energy-based. It's good at predicting pore pressures up to nearly the time that liquefaction occurs, but it's not very good after that time because it will over-soften a soil deposit. We'll talk about that kind of mechanism. It's not the only code that does that, but it illustrates a deficiency that the developers of the program are in the process of addressing. One of the nice things about doing these kinds of analyses is it allows you to look inside the liquefying soil layer and see how the effective stresses, pore pressures are changing, to see what the stress strain behavior looks like. And we'll talk a lot about this phase transformation behavior tomorrow, but we'll see that it can cause a soil layer to stiffen within a cycle. And that can lead to these dilation pulses that we see in some of these ground motions. So more of this will be discussed tomorrow. So to summary, when we're doing one-dimensional analyses, whether they're equivalent linear analyses or nonlinear analyses, we have to make sure we're aware that they're one-dimensional analyses. We're looking at one-dimensional wave propagations, only going in one direction. We're assuming that the layers extend infinitely in the horizontal direction. So they're all in phase. When the motion, the profile is going back and forth, it's going back and forth everywhere. There's no variability in the soil conditions laterally. We're assuming they're constant. And in reality, we know that even in a pretty uniform material, the properties change at the same depth. They're not uniform horizontally, and they're certainly not uniform vertically. And so we can get concentrations of stresses and strains occurring because of the assumed uniformity that wouldn't necessarily really occur in practice. So we have to keep that in mind when we're looking at, when we're performing these analyses and when we're interpreting their results. They're particularly useful for profiles where we have high impedance contrast, where we have significant differences in the stiffness of different layers. If you have a very generic soil profile that has a velocity profile that's compatible with the database, the average of the databases that say GMPEs are based on, your analysis, your site-specific analysis will give you results that are pretty consistent with the results in terms of amplification that you get from a GMPE, a ground motion model. Now, the ground motion model is not going to tell you what's happening below the ground surface. There are a number of advantages that you get from a site-specific analysis. But if you're just looking at response spectral amplification, you're probably not going to get a result that's much different than you get from the GMPE, if that's all you happen to be interested in. Nonlinear analyses, at least good ones, that handle damping, low strain characteristics properly, can match equivalent linear analyses when the strain levels are small and there's not much nonlinearity. But when we have high strain levels due to very strong shaking or very soft and weak soils, nonlinear analyses will give us better results. We have to make sure we're accounting properly for the strength of the soil, because we're going to be generating large strains. Strains more than the 0.5 to 1% level that the resident column is giving us reliable properties for. We can handle pore pressure generation if we have the right kind of constituent model in our 1D analysis. We can predict permanent deformations. And we do that very commonly for two-dimensional analyses, more so than for one-dimensional analysis, which would normally apply to level ground conditions. And we have to account for the strength of the soil. Now look at that, it's my first and my fourth trip, so it must be important. Okay? That's the end of the nonlinear presentation. I think that's the end of today's presentations. I guess we've got ourselves back on time and maybe even a little bit ahead of time. I'll hang around for a little while. Are there any general questions that anyone would like to ask? If not, we'll be around when Zach here.
When it comes to liquefaction and excess pore pressure dissipation, there is commercial software that allows you to perform equivalent linear analysis in order to determine those specific responses. You mentioned that we are expecting higher strains. We are expecting we want to focus on liquefaction and excess pore pressure dissipation. We should go for non-linear. What happens when we have this kind of situation, when we have this equivalent linear in the consultant office, which is more often realize that a non-linear analysis? What is your thoughts about that situation?
Well, my thoughts are we should remember that equivalent linear analyses are total stress analyses. So there's no way to calculate pore pressures within an equivalent linear analysis. Okay? Now, you can calculate, say, some amount of dissipated energy or use some external process to try to relate the pore pressure that you relate this response of your model to some estimate of what the pore pressure would be. There are energy-based methods. You might calculate a factor of safety and use a factor of safety to estimate what the pore pressure might be. But that's really a poor way to practice. I would not recommend doing that at all. We have the ability now to predict pore pressure generation within a nonlinear analysis. That's something that we would have done 30 or 40 years ago. But it's not something we should be doing now. So if somebody's doing things that way, that's pretty poor practice in my view. It could be done a lot better. We have the tools to do it a lot better. And should be doing better than that. I don't know if you want to comment any further on that, John. Looks like an agreement with the thumbs up. That's my opinion. I think most people who are involved with liquefaction evaluation would say the same thing.
Here you said that S software produces different response compared to OpenSys and their software. So I was wondering if the response is like higher or lower.
Sorry, can you hold it a little closer to your mouth? When you-
No.
Thanks.
So my question is, you said that the software produces a different response compared to the analysis you can do in OpenSys and Deep Soil and other software. So I was wondering, at low frequencies, is this response higher or lower? And if this is related to the fact, I heard Dr. Spike talk on Rome. But he said that sometimes he finds layers that won't liquefy. He does the analysis with the code that he's developing now with S2. And so I was wondering if this different formulation of the uplink is related to those differences that he's finding or there are other causes.
Well, we'll talk in some detail tomorrow about analyzing liquefiable soil deposits. The main differences that we see are between models that simply calculate pore pressures and we use it to soften the backbone curve, and they soften it monotonically until there's almost no stiffness at all. But in reality now we understand much better this idea of phase transformation behavior that results from the volume change characteristics of soils that Professor Gray talked about. And we can capture that in our constituent models now and show that even though the pore pressure can become very high and effective stress can become very low, that upon additional shear stress, the soil will dilate and the pore pressures will go down, the effective stresses will go up, and the legs will come on, and the soil will become stiffer. And if you don't model that, you really make some come to some inaccurate conclusions about how the profile is going to behave. You can show that you'll essentially isolate the upper soils from the ground shaping. I got pulled in, this was maybe 10 or 12 years ago, to a project where there were two potentially liquefiable layers, and people ran an analysis using a program that operated in that way, and the lower layer liquefied and became so soft with the computer program that no energy got through that layer up to the upper layer. And they were very happy about that because then they didn't have to do any improvement for the upper layer. Well, there were two major problems there. One is they were forgetting that they were doing a one-dimensional analysis and that waves were only coming up vertically. In reality, this was in kind of a basin, in a sense. It was a valley that had been filled in. And so there were going to be waves coming in from other directions as well that could bypass that lower layer. And the second was that layer is not going to become as soft as their model had predicted it would be. And so this dilation would cause additional waves to travel upward and go through that layer and cause liquefaction of the upper layer. So I took the program I was working on and analyzed it and was able to show that pretty clearly. And so it led to a big difference in the way that particular, it was a bridge over this area, was going to be designed. So we'll talk more about the modeling of liquefiable soils and the response of liquefiable soils in one of tomorrow's lectures.
One question here regarding one of the presentations.
I don't think your microphone is on.
I'm sorry. I'm sorry.
I don't think my ears are on.
So I have a question regarding one of the presentations at the beginning. Professor Bray was saying that he prefers a probabilistic seismic hazard analysis or assessment than a DSHA. However, that consideration still goes on if the calculation you make is for a return period of 10,000 years, because at some point you have to cap the probabilistic analysis. I'm not sure if that the response is the same if for different return periods, because if you are going to analyze a dam, I don't know if a PSHA will provide you a good answer, because the tail of the probabilistic curve is going to be so important, and I'm not sure if to have like 6 standard deviations is something that is realistic to obtain a result.
A well-run probabilistic analysis is always better than a well-run deterministic analysis because it includes all of the uncertainties and it brings in time. In the 1980s, people gave up on the Feinman method in geotechnical engineering because it was run poorly. And they said it's so hard to model soil and nonlinear response. This idea of using Feinman method that was developed by the structural engineers in geotechnical engineering makes no sense. But we realized we just needed to do a better job. And now we confidently use advanced numerical analysis, such as Feynman analysis, finite difference analysis, to do analysis. The probabilistic analysis method got started, it had good underpinnings, but it got misused, wrongly used, and it got some ridiculous answers sometimes. It's the right way of doing it. The key is to make sure it's done well. I do think for critical structures like dams, it makes sense to look at some key scenarios deterministically to check yourself. But remember, when you do a deterministic analysis, you are saying you have 100% confidence it's going to be that magnitude, that distance, and that level of ground shaking given that magnitude and distance. You are doing a probabilistic analysis, you are just putting 100% weight on one logic tree. A probabilistic analysis allows you to be more realistic by saying it could be different magnitudes, it could be different distances, and very importantly, it could be different levels of ground shaking given that magnitude and distance. It needs to be checked because it's a lot of calculations, but each calculation is actually relatively simple. If you have a probabilistic analysis done, make sure they de-aggregate the hazard, and does it make sense? Look at things about how they're modeling the sources, and make sure that that makes sense. Make sure they give you the logic trees, and they tell you all the weightings they're doing, and all the decisions they're making, but you can force them to do a good job.
I'll add a little bit that applies to some special conditions, I think. And it points out the importance of looking at de-aggregations, where we're going to break down the contributions to hazard, the hazard that we calculate in the probabilistic analysis, by magnitude and by distance to see which combinations of magnitude and distance produce the greatest response. But we also break them down according to this parameter epsilon, which tells us how many standard deviations above or below the median we are, how rare our ground motion is. Now, if we're looking at a very critical structure, and this happened in the US with a nuclear waste disposal project, we may be looking at a very long return period. That is, we want to design for a motion that would be very, very rare, 10,000 years, maybe longer than that. Okay, so it's a very strong motion. If you look at the de-aggregation there, the de-aggregation is going to force everything towards a very large earthquake, very large magnitude at a short distance. That's what will come out of a de-aggregation analysis. And then you're going to start forcing epsilon to a higher and higher and higher value, which means you're looking at an increasingly rare motion. Now, we make the assumption that ground motion parameters are log-normally distributed, that their logarithm is normally distributed. And for most of the practice that we do, that seems to be pretty accurate. But if we're going way out, multiple standard deviations, it's not necessarily so accurate, and we don't necessarily know how accurate it is because we don't have extremely rare ground motions very accurately. So in some cases, we'll truncate the distribution at 2 or 3 standard deviations. Sometimes we'll use different distributions, extreme value distributions, things of that nature to try to more accurately characterize it. For this nuclear waste disposal site, they had peak accelerations that were something like 7 or 8 Gs. And the rock would fracture before that happened. You have a physical limit to how strong the shaking can be. So for those kind of extreme cases, then we may use deterministic analyses as a cap or a reality check or kind of a maximum that is defined more by policy, I think, decisions than engineering decisions at that point.
But don't you agree that that's when you get out to the extremes? When you get into the 30-year return period, the 50-year return period, the 475-year return period, those are still fairly well described by the probability distributions that we're using.
Well, yes, I certainly agree with that. And for 99% of the cases that we deal with in regular civil practice, it works quite well. But that is the exception, I think, to the rule, at least regarding that particular issue.
And I think use both. I do deterministic analysis as well, but I think you want to use both so that you can play them off of each other. But the future is clearly, as we go on for both low return periods and intermediate return periods, and even the large ones with physical checks on it, the probabilistic method, because it allows us to look at a lot of possibilities and weight them by what we think is reasonable. And that's better than just putting all of our confidence that only one thing's going to happen.
Una pregunta con respecto al tema de la tasa de recurrencia en la evaluación de la curva de recurrencia de magnitudes. Esa tasa de recurrencia está valorada como función de una ventana de tiempo, de un tiempo, pero uno tiene unas bases de datos que pueden tener, historia de 500 años, de 200 años, o de 100 años o menos. ¿Cuál es el tiempo correcto que se debe tomar para determinar ese lambda o esa tasa de recurrencia?
Well, there's the return period that we use for design, and that is generally set by building codes. In the U.S., it was set at a return period of 475 years for many years, a long period of time. Then it was changed to, and that corresponded to a 10% probability of exceedance in a 50-year period. That was then changed to 2% probability of exceedance in a 50-year period. It was thought that the 10% probability was creating motions that were too weak in the central and eastern United States. And so they decided to increase the hazard level or increase the return period. That in the western United States caused an increase of about a factor of 1.5. And so the structural engineers that made this decision just looked at their data and they said, well, our structures have about 50% more strength as they're constructed than as they're designed. So they divided by 1.5 or multiplied by 2/3. And so we ended up in California, where the people who made these decisions were mostly residing. We ended up with about the same level of shaking there. It increased the structural demands in the central and eastern United States, but it had an unintended consequence with respect to geotechnical engineering, because all of a sudden the geotechs were asked to design for a higher level of shaking than the structures were. Is that consistent with your
But
understanding of it?
my interpretation of your question is you're looking at the catalogs used to develop the recurrence model. And so I think you're asking about how do you judge completeness. There are seismological rules for looking at magnitude bends of, 3 to 3.5, 3.5 to 4, 5, 4 to 5.5, 4.5, and 4.55, and so on, where you look at the historical record, you have to do a lot of declustering, you have to do a lot of things to make sure you have a good catalog. And then, especially for the lower magnitudes, they tend to be incomplete, because the records didn't pick that up. The historical record actually does a better job with some of the larger earthquakes. And so there's completeness analysis that's done, declustering analysis, to try to get a good historical catalog. There'll be some deficiencies, and there's ways to make up for that. Then you have to look at the geologic data and complement that, and that's why you end up with either a truncated exponential, if it's only based on historical catalogs, or you end up with something like the characteristic earthquake that is a two-part model. But this allows you to at least do the best we can do. And I've worked on projects where we have a lot of information, and it's done incredibly well. 2 projects I've worked on in Mozambique, in Africa, and in Myanmar, where this was really difficult. And so the seismologists and geologists and myself as a peer reviewer really had to work hard to come up with something that we thought was reasonable. And in the end, because we disagreed, we ended up with 2 different models, and we weighted them by our relative confidence. What else can you do?
I'm sorry, I didn't understand your question. It was a good answer, but to the wrong question.
Buenas noches. Es una pregunta corta. Respecto a las curvas de recurrencia, interpreto que esas curvas es la suma del aporte de varias fuentes tectónicas. No es más sensato, no es más coherente generar espectros de respuesta de cada fuente tectónica y obligar a los ingenieros estructurales o diseñadores de presas, etcétera, a que hagan los análisis para varios espectros de respuesta y no solamente a uno genérico, promedio. Gracias.
I think that does make some sense. From a pure probabilistic sense, we sum the contributions from all of the individual sources, because we don't know which source is going to contribute the ground motion that we're concerned with. However, the conditional mean spectrum kind of does what you're talking about, in that it allows us to develop separate ground motions for say a very large magnitude event that's controlling the long period part of our spectrum, a small localized earthquake that would control the short period and high frequency part of the spectrum, and in some cases an intermediate event. And so in Seattle, where I am, we have 3 main sources, and we generally will produce conditional mean spectra that are consistent with each of those 3 sources. So we don't formally break them down and say that we're going to have a design spectrum for a shallow crustal earthquake, and another one for a deep intruncate earthquake, and another one for the great subduction earthquake. But we achieve something that's similar to that by use of the conditional mean spectrum.
¿Alguna pregunta adicional? Muchas gracias a todos por acompañarnos hoy. Thank you to Dr.